Hello. Wait, let me connect my hotspot to the computer. Hello, hello. Yeah, because my Wi-Fi is kind of laggy, so let me connect to my hotspot really quick. Okay, so for today's midterm 2 review session, we're gonna go over how to choose between SN2, SN1E1, and E2 reactions, and do a lot of practice rounds with that, and then go over the problems in the practice midterm and any other topics that you guys want to go over. So, first, let's go over the different types of nucleophiles and electrophiles, right? And there is a slight and subtle difference between a nucleophile and a base, right? And then at the very end, this summary chart here could be used to help you guys predict the product for these kind of reactions, depending on what kind of substrate you have, what kind of base, what kind of nucleophile you have, um, and then it will tell you what kind of reaction you have. No reaction, SN2, E2, Zaitsev, E2, Hoffman, or SN1, E1, right? So a nucleophile is going to be nucleus loving, right? And we know from Gen Chem that nucleus is composed of protons and neutrons. So you could think of it as positively charged, right? So nucleophiles, they tend to have a partial negative or full negative charge, right? So this chart right here will be posted in the notes, or you can screenshot it right here, right now. But I'll post this in the review session notes after works for you guys to review. Yeah, and we could go over IR spectrum tips as well, like how to determine the functional groups looking at the IR, and a lot of practice problems with that as well. Okay, so nucleophiles are partial negative charge or negatively charged, which would attack electrophiles, right? Because electrophiles are going to be either partially positive charge or fully positively charged, right? A base is going to be something that accepts or attacks a proton, right? And they are also partially negative or fully negative charge, because to attack a proton, the base has to have a pair of electrons, right? So here is the different types of nucleophiles and bases. Types of nucleophiles and bases, right? Right. You could either have a strong nucleophile or you could have a weak nucleophile, right? Does your professor allow note cards on the final exam? Or I mean the midterm, this upcoming midterm tomorrow? Yeah, okay. So I would recommend including this chart in your note card, because it will help you decide what kind of reaction you have. Like just by looking at the chart without understanding like the reasoning behind it. But it's best to understand the reason behind why these reactions go the way they do, because it will help you in the future chapters, and help you like connect the future chapters to the old material, right? Instead of just brute force memorizing the factors and what reaction it gives you, right? So what do you guys think weak nucleophiles are? Are they going to be uh, neutral charge or negative charge? Let's compare a molecule that is neutral charge and a molecule that's negatively charged. Which molecule is a stronger nucleophile. Yeah, SN will stand for substitution, and E will stand for elimination. So something that is negatively charged will be a stronger nucleophile than something that is neutral charged, right? Because it has more electrons.
What? I heard the scream. What? What? What?
Why did the rats be here on this fence? When they fell out of the tree, this tree, and then they went down. And
Okay. Because something that's negatively charged will have an excess of electrons, and that excess of electrons is going to be a strong nucleophile because it will be able to attack something that's positively charged, right? The easiest thing to remember are weak nucleophiles and weak bases, right? And then we could abbreviate that as WBWN, weak base, weak nucleophile. And there's only two that you need to know: neutral water molecule, H2O, and neutral alcohol, ROH, where R can be any hydrocarbon chain. It could be ethyl, methyl, isopropyl, any random hydrocarbon chain. Right. So that's the weak base, weak nucleophile. Now, when we have a strong nucleophile, wait, let's fix up this chart. These are going to be the types of nucleophiles. Nucleophiles, right? Because when you have a strong nucleophile, it does not have to be a strong base. It could be a weak base. So for example, let's say we have a strong nucleophile, but weak base, right? Say weak base. And we're going to abbreviate this as weak base, WBSN. Weak base, strong nucleophile, which is different than WBWN, right? And these ones here are CN minus, N3 minus, your halides, Cl minus, Br minus, I minus. You could even see H2S, sulfur, and H3, neutral NH3, and some phosphorus things, etc. Right? But most likely you will see like NaCN or KCN or NaN3 or KN3, right? Because whenever you see Na or K, think of it as a spectrated ion. That's always positively charged. And whatever is attached to the Na or K is going to be negative charge. So NaCN, the CN will have a negative charge, right? Okay, so that is a weak base, strong nucleophile. The other type could be, let's say you have a strong nucleophile and it's also strongly basic, right? It's also a strong base. But there's two different types of strong base, strong nucleophiles you have. You can have a small unhindered one. So let's say we have that. This, let's say small, unhindered, strong base, strong nucleophile. Right. These ones here, the way that I like to remember this is any atom, like any oxygen that's negative charge, so OR minus, HO minus, and any nitrogen that's also negative charge. So it could be NH2 minus, R and H minus, or even R2NH, right? So the best way to remember the small unhindered strong base strong nucleophile is that if you see a negative charge on an oxygen or a nitrogen, then that's a strong base strong nucleophile, or SBSN. Right. The other type that you might see is a bulky, hindered, strong base strong nucleophile. And there's two that you need to be familiar with. Tert-butoxide, which is this. You might see this in the form of CH3, 3COK or Na, or you might see it as TBU, OK, or Na, tert-butoxide, right? And it's bulky because the R group here is sterically hindered. There's a lot of groups surrounding that negative charge right there. And the other bulky base that you need to be familiar with is LDA, right? I think you just need to recognize the three-letter base, but what it looks like is this right here. where we see that this is a strong base because this nitrogen here has a negative charge, right? And it's bulky because we notice that the R groups are sterically hindering the negative charge here. So these are the two bulky bases that you need to be familiar with. Right. So here are the types of nucleophiles and bases that you need to be familiar with. Say this is the strong base, strong nucleophile, small. This is the bulky, strong base, strong nucleophile. So there's 1, 2, 3, 4 different categories, right? Okay. So yeah, there's actually a lot of like concepts to go into this. So to save time, what do you guys want to go over? Like go straight into the practice problems of the midterm, or go over some of these concepts here for SN2, SN1, E1, or go straight into those practice problems, like, and then show you guys my thought process. Okay, yeah, let's do practice. Let's do practice. Yeah, this is like way too much. Okay. So let me give you guys some practice problems on this. Let's give you guys 5. Yeah. And also draw the mechanism for these reactions as well. Actually, I might give you guys six of them. Okay, last one. Okay, yeah, Fisher projection as well. Yeah, let's do that. So let's actually make this last one about the Fisher projection. Okay, so let's do these practice problems here. What did you guys get for the first one? What was the thought process for the first practice problem here? Let me add more space. And feel free to get it like wrong as well, because other people might have the same like problem or question, and then that's how you guys can like learn to avoid them for the midterm tomorrow. Okay. Yeah, SN2 reaction. And here's the thought process on how to do it. The 4 things that you have to look out for are the type of substrate that the reactant has, the type of attacker you have. So is it a strong base, strong nucleophile, weak base, weak nucleophile, or weak base, weak nucleophile? The type of solvent would, and then the type, is it a good leaving group or not? Right. So the last 2 factors here are actually less important because that is not as distinguishing as the first 2 factors, the substrate and attacker. So, okay. So the type of substrate, to determine that, look at the carbon attached to the leaving group, right? We do have a good leaving group, which is bromine. And this is the substrate right here attached to the good leaving group. You could call that the alpha carbon, right? Then we have to see how many other carbons that alpha carbon is attached to. We see that this alpha carbon here is attached to 2 other carbons, 1, 2. So this is a secondary substrate. Right? The type of attacker we have here is NaN3. NaN3 is a weak base good nucleophile, right? NaN3 is a weak base weak nucleophile because whenever you see Na, always ignore that because that's a spectator ion. It always has a positive charge, which means that the N3 is a negative charge. The N3 minus here is a weak base strong nucleophile, right? And the type of solvent here, if you see random letters like DMSO, DMF, THF, all like any of those random letters, this is an aprotic solvent, right? But these 2 factors here are the ones that you're going to use in the table right here, which we said our substrate was secondary. So we look at this row here, and then we said it's a weak base weak nucleophile because we have N3 minus, which is over here. This N3 minus is a weak base weak nucleophile, which we have to look at this column here, giving us an SN2 reaction, right? Yes, aprotic and protic solvents will have different effects on the reaction, or SN2 reactions prefer to be in aprotic solvent, and SN1E1 prefers to be in protic solvent. And the reason why SN2 prefers to be in aprotic solvent is because this N3 minus here is a nucleophile because it's negatively charged. This alpha carbon right here attached to the leaving group, it's partially positive charge because it's attached to this really electronegative atom, bromine, right? So that's the electrophile. In OChem, nucleophiles always attack electrophiles, right? So this negative charge nucleophilic component here is going to attack that electrophile, and then we're going to kick out that leaving group, right? But do you guys remember the mechanism for SN2 reactions? Like what happens in SN2 reactions? Oh, these practice problems are like I just make them on the spot, right? But I can send you guys practice. Levin's practice worksheets are really good for these reactions as well, right? And we can do Kahoot on these as well after the practice midterm. Inversion, right? Or backside attack. Can we determine which process we have to use by looking at the solvent? Don't rely on the solvent only as the factor, because I've seen some SN2 reactions that happen in protic solvents before, right? And I've seen some E2 reactions that can work on both aprotic and protic solvents, right? So like the solvent is not as a big factor as the substrate and attacker. Probably the most important factor is the attacker, the type of base and nucleophile you have. Is it weak or strong, right? And then the substrate will follow along with that, right? These 2 here are not as important. I wouldn't worry about those 2. I would worry about the top 2 for this table right here. Right. So because this is an SN2 reaction, we're going to do a backside attack or inversion of stereochemistry. Right. So that dash will convert to a wedge, which is going to be a wedge N3. There we go. Right. And let me actually make this a chiral center because is this a chiral center or not? Like this carbon here, is this a chiral center? No, it's not a chiral center, right? So you don't actually have to put a wedge or dash here because you only need to do that for chiral centers. So let me actually make the problem more accurate by putting a methyl group right there. There you go. Right. So SN2, right? Weak base, weak nucleophile. And let's look at the substrate here. Notice how in the substrate, it worked for methyl, primary unhindered, primary hindered, and secondary substrates. Do you guys know the reason why SN2 reactions prefer less substituted substrates? Like, what's the mechanistic reason behind why SN2 reactions prefer less substituted substrates? Steric hindrance, more space, right? This nucleophile here, N3 minus, it's going to want to attack that electrophile, but in order to do so, it needs to have less steric hindrance, right? If this was tertiary, for example, then that would create too much steric hindrance, less space for this nucleophile to come in and attack, right? More room for backside attack, right? And the reason why SN2 reactions prefer to be in a product solvent as well is because in a product solvent, there are no hydrogen bonds that are going to interfere with this ion attacking, right? Because if there were H bonds around, like let's say we have like a lot of partial positive H's around, it's going to create a salvation shell around that nucleophile, blocking that nucleophile to attack, right? And this is in product solvent, like water or alcohol, right? Which is why we want to do this reaction in a product solvent to avoid that salvation shell and blocking that nucleophile to attack the electrophile there. Right, nice. Okay, let's move on to number 2. What reaction do you guys think this is? Well, first, before that, let's do the four things. What kind of substrate is this? Reactant here? Secondary, right? Because the alpha carbon or the carbon attached to the leaving group is bonded to 2 other carbons. Nice. What type of attacker is this? This ethanol. You guys can look at the list here too. Weak. Weak base, weak nucleophile, right? Because if it is weak base, it could be a strong nucleophile, which is this list right here, right? But ethanol or any alcohol is not on that list. So do not use this weak base, strong nucleophile column here. But it is a weak base, weak nucleophile, which is this ROH here, this alcohol here, which means that we're going to use this column here of the table, right? And because we said it's secondary, we're going to use this row right here to show that it is a SN1 reaction. That's our reaction right there. Right, SN1 or E1, they go together. Right. So it's a weak base, weak nucleophile. The solvent, if you see no other solvent, the solvent is the reactant itself. And it's protic because we have an H bond here. This hydrogen is attached to either one of these 3 atoms, fluorine, oxygen, or nitrogen, a very, very electronegative atom. So that is a protic solvent. And the leaving group, we got a good leaving group, fluorine. So that's good right there. Right. Okay. So for SN1 and E1 mechanisms, what do you guys think is the first step that happens in the mechanism? What is the very first arrow that you're going to draw in the mechanism for SN1, E1? Yeah, get rid of the leaving group. So this good leaving group here is going to leave. And the reason why it's able to leave by itself is because of the protic solvent here. A lot of partial positive hydrogens from the ethanol are going to surround that good leaving group and solvate it and grab it away, making it leave by itself, right? Once it leaves by itself, what is our intermediate here? What is this carbon's charge when it lost the bond? +1, right? Which is a carbocation. And whenever you have a carbocation intermediate, you always have to look out for what step. This is the step where most students forget in the mechanism or reaction: hydride shift or methyl shift, right? So carbocation rearrangement. And there are 2 types of carbocation rearrangement steps. The more common one is hydride shift. The less common one is a methyl shift. Right. We see that this carbocation here is secondary, right? And yeah. Let me explain why it shifts. I was gonna if you guys knew this concept already, so that's good that you asked that question. So the shifts here are going to happen because of something called carbocation stability, right? So let's have the least stable carbocation, which is a methyl one. This carbon here with no R groups, just 3 hydrogens. Then let's look at a primary carbocation. This carbon here is primary because it's only attached to one other carbon. And then we have a secondary carbocation because that carbocation there is attached to 2 other carbons. And then we have a tertiary carbocation. Right, because this carbocation here, the carbon with the cation or positive charge, is attached to 3 other carbons. Right, the more substituted the carbocation is, the more stable it is going to be. And there is a term for that. There is a reason for why the more substituted the carbocation is, the more stable it's going to be. Do you guys know the reason why that is the case? Starts with a H. Hyperconjugation. Right, nice. Right, because think of these bonds here as full of electrons that are able to inductively donate electrons to that carbocation, right? The more groups it has, the more hyperconjugation it has, making this carbocation more stabilized by the negative charges, right? The way that I like to think about this is that the more friends it has, the more stable it's going to be. Yeah, the more friends it has, the less lonely it's going to be, the more happy it's going to be, more stable it's going to be, right? We see this tertiary carbocation here has the most amount of friends, so it has the most hyperconjugation, the most stability. Whereas this methyl group here has no R groups at all supporting this carbocation, making that the least stable carbocation, right? In 118b, when you guys learn about alkenes, there is something that goes like that that's more stable than the tertiary carbocation, which is something called this is a methyl carbocation right here. This is a primary carbocation. This is a secondary carbocation. This is a tertiary carbocation. This is a secondary allylic carbocation, which is what you guys will learn in the very first section of 118b, right? And you guys already learned the reason why, though, why this structure is more stable than this structure. Can you guys think of any reason why that you guys think this carbocation is more stable than this structure here? Think about what's around that carbocation and what it could do. Resonance, right? We see that this double bond here can move to make a double bond right here to get this resonance structure here. And because we see that this positive charge here is delocalized, meaning that it's able to move around that whole structure, that is a way more stabilizing factor than hyperconjugation. Resonance overpowers hyperconjugation, right? You're gonna notice that pattern. Resonance is like king. It's like the most important factor for these chapters and concepts, right? Okay, so we see that this carbocation here, yeah, it's gonna be the double bond here that can do resonance. The double bond there is the pair of electrons that are moving to make a double bond between this carbon and this carbon here. And when it does that, this carbon here that used to be the positive charge is now neutral because it gained the bond. But this carbon here gains a positive charge because it lost the bond, right? Before that carbon had 4 bonds, but now that carbon only has 3 bonds. It lost the bond, giving that carbon a positive charge. And that checks out because these resonance structures have to have the same charge. The charges have to conserve, right? So if we go back to the mechanism here, we see that this is a secondary carbocation here. And when we do these carbocation rearrangement steps, we can only shift the carbocation one to the left or one to the right. Which position do you guys think the carbocation can be more stable at? The one to the left or the one to the right? The one to the left, right? Because we see that if it's here, it is tertiary, making it more stable. But do not do this in the test, right? Do not draw that positive charge moving to the carbon there and saying that it creates this structure here, right? What's the problem with that arrow? What's wrong with that arrow? Yeah, arrows should move electrons. Yeah, so the electrons could be a pair of electrons. They could be a double bond. They could be a triple bond. This carbocation here has no electrons at all. So do not draw that arrow in the mechanism, right? Right, it's an electron pushing arrow. And there are no electrons here to push. No electrons there to move. So that arrow will not happen, right? But when you do draw this mechanism here, explicitly draw out that invisible H bond, right? Where this whole bond attached to H right there represents 2 electrons, which is going to migrate, that whole bond is going to migrate onto that carbon there with the positive charge, with the carbocation, right? And I'm going to highlight that H yellow to show where it moved, right? And I'm just going to draw out that H right here. That H moved right here, right? Because this carbon gained a bond, it now has 4 bonds and it's neutral. This carbon here, it used to have 4 bonds, 1, 2, 3, 4. But because of the hydride shift that we just did, it lost the bond. It only has 3 bonds now, which is why it has a positive charge, right? And that's the reason why we do a hydride shift, to get to the more stable carbocation. This is a tertiary carbocation, which came from a secondary carbocation. Yeah. Let's say that we're trying to do an SN1 reaction here, because SN1 and E1, they go together. What would be the next step in the mechanism if this was an SN1 mechanism reaction? So hydride shifts are not always going to be there, because let's say you have this practice problem right here. And then you react that with water. The leaving group would leave first in the mechanism, form a carbocation there. If you look to the left and right of this carbocation, which is secondary, the left is also secondary, the right is also secondary. So in this case, both cases are equally stable, so you do not do a hydride or a methyl shift in this example. But in the examples where the carbocation can become more stable, then that's when you always have to do the shift, the hydride shift or methyl shift, right? So whenever you have a carbocation intermediate, always look out for the sneaky step of carbocation rearrangement. This is the step where most students forget about for SN1 and E1, the carbocation rearrangement step. Right. Are E1 reactions the same process as E2 reactions, but with different products? So E1 and E2 are going to be similar in that both of them are elimination reactions, right? Because of the E there. E1, E2, E, elimination. And all elimination reactions will create a double bond or an extra bond, a pi bond, right? So E1 and E2 reactions will create double bonds, but the mechanism is different. One reaction will have only one singular step, the other reaction will have multiple steps, right? Which one, E2 or E1, will have one step? And then the names are kind of confusing because it could be misleading, right? Yeah, E2 has one step. Even though it has a 2 there, it only has one step, right? And is it unimolecular or bimolecular reaction? Bimolecular reaction, right? And what does that mean? What does a bimolecular reaction mean? Yeah, the reaction rate would depend on 2 molecules. The reaction rate would depend on the nucleophile concentration and the substrate concentration, right? Unimolecular will only depend on one concentration, which is the nucleophile. Oh no, the substrate concentration, right? Unimolecular reactions only depend on one substrate concentration, which is the substrate, not the nucleophile. The nucleophile doesn't matter. If you increase the nucleophile concentration for a unimolecular reaction, it will not change the reaction rate. But if you increase the substrate concentration for a unimolecular reaction, then the reaction rate would increase, right? How do you know when we will have a carbocation intermediate, right? So carbocation intermediates will always be formed for SN1 E1 reactions. All of these reactions here, SN1 E1, always form a carbocation intermediate. So that's the other way to remember these reactions. SN1 E1, they always form a carbocation intermediate because the leaving group leaves first. Yeah. Yeah. Okay. So leaving off of this like intermediate here, let's say we have an SN1 product, SN1 reaction. What is the next arrow that you're going to draw in here? Yeah, ethanol will attack the carbocation, where specifically this oxygen with a pair of electrons will be the nucleophile that attacks that carbocation right there, right? This pair of electrons here, those two electrons are going to make a bond between this oxygen and carbon here, right? So what I like to do is I like to star my attacking atom, which is this oxygen here. That oxygen is going to attack the electrophile, and I'm going to dot the electrophile. That's the electrophile right there. In this reaction, a new bond is going to be formed between the star and dot, right? Star and dot. That's the new bond between them, right? New bond between nucleophile and oxygen, nucleophile and electrophile. The star was an oxygen, so we can make that carbon. We have to make that an oxygen. And then at this point here, this star oxygen here is attached to two things: an ethyl group, which is this ethyl group here, and a hydrogen, right? It still has this pair of electrons that was not reacted with up here, right? But it lost its pair of electrons when it attacked that carbon right there. That pair of electrons became this new bond right here. That new bond came from that pair of electrons right there, right? What would be the formal charge of this oxygen here with 3 bonds and a lone pair of electrons? Positive charge, right? Now there's one last step here to get to the final product. What do you guys think the last step is to get to the neutral stable product? How can we neutralize that positive charge? Yep, get rid of the H. Deprotonate the oxygen. Right. Another ethanol, because we will have excess amount of that, will come around and deprotonate that hydrogen right there. This ethanol here will serve as a base, which attacks that H. This bond between the oxygen and H has 2 electrons. Those 2 electrons are going to go onto that oxygen right there when this base rips off that hydrogen from that oxygen, right? Which is why it will now have 2 pairs of electrons. It gained an extra pair from that bond right there between oxygen and hydrogen, right? But this ethanol right here acted as a nucleophile. It acted as a nucleophile because it made a new bond with the electrophile here, right? But this ethanol here acted as a base in the mechanism because it grabbed a hydrogen. Bases grab hydrogen. Right. So this is the SN1 product here. Right. Okay, have you guys learned about alkene stability yet? Like, let's say, wait, let's say we have these different alkenes here. The more substituted the alkene is, the more stable the alkene is going to be. Right. Now, this is an unsubstituted alkene. This is a mono substituted alkene. These 3 here are your di-substituted alkenes. This is your tri-substituted alkene, and this is your tetra substituted alkene, right? It's basically saying how many groups other than hydrogen are attached to the alkenes. This is considered unsubstituted because all of the groups attached to the alkene are hydrogens, right? This is mono because there's only 1 R group attached to it. This is di because there's 2 R groups. Tri, 3, tetra, 4, right? Specifically, this right here is called geminal. This is cis, and this is trans, right? Geminal and cis alkenes will have similar stability, but trans alkene is going to be more stable than cis alkene, right? Because of steric hindrance, right? So the product of the SN1 product that we did is going to be this right here. SN1. A lot of students would have put this as the answer instead. Right. Right. This right here would not be the answer, would not be the major product. Right. A lot of people would put this as the answer because they would forget about the hydride shift and just have the ethanol attack the carbocation right away without the methyl shift, leading to this minor product here, the wrong answer here. So that's SN1. Okay, so let's move on to E1 now. Does this have the oxygen on top and bottom? Oxygen on top and bottom. So for the product here, we only have one oxygen here. Oh, are you talking about the reagents here, or like what do you mean by top and bottom? Like if it's a wedge or dash. Yeah, that's a good point. Right. Because once we have this carbocation right here, when this nucleophile attacks, first, what is the hybridization of this carbon here? SP, sp2, or sp3? Yep, it's sp2, which means that it is going to be flat and planar. That's the geometric shape of that carbon, flat and planar. Right. And because it is flat and planar, when this nucleophile comes into attack, it could attack on either side. It could attack the top side, giving you a wedge product, or it could attack on the bottom side, giving you a dash product. So you could have written that as the answer, or you could have written this as the answer. Well, in this case right here, is this a chiral sensor? This carbon here? No, right. It's not a chiral sensor. So in this specific case, we cannot say racemic mixture, because what is the definition of a racemic mixture? Equal R and S, or a 50-50 something between yeah, enantiomer enantiomers, 50-50 mix of enantiomers, 1-to-1, right? These are not racemic in this specific example because there are no chiral centers, no enantiomers here. If we don't have a chiral center, we can't have stereoisomers, right? No chiral centers. Now, if I added like a methyl group there, boom, 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 boom. Now these would be enantiomers, and they would be racemic mixtures, right? Because there is a chiral center here now. So be careful of that as well. Okay, yeah. Okay, so crowded. Let me go here. So let me make a note. SN1 and E1 will have the same mechanism up until the most stable carbocation intermediate. Right. So we could speed run the beginning mechanism because we already did it for SN1. So this is going to be E1 now, focusing on E1. Leaving group leaves, form a carbocation at where the carbon lost the bond. And at this point here, whenever we have the carbocation intermediate, we always stop and think if we could do a hydride or methyl shift, which in this case we can do, moving the hydrogen there to form the more stable tertiary carbocation right here. Now, at this point here, it could diverge into the SN1 product, or it could diverge into the E1 product. We already did the SN1 product, so now let's do the E1 product. The E1 product is elimination reaction, which I said earlier that it forms a double bond, right? Now, to choose the carbon that would get deprotonated, right? You first locate your alpha carbon. The alpha carbon is the carbon attached to the carbocation. Your beta carbons will be the carbons attached to the alpha carbon, one away, right? Or you can think of it as two away from the carbocation, right? Draw out all the beta hydrogens here, and let me label this A, B, and C. Which one of these beta hydrogens do you think is going to get deprotonated to form the more stable alkene? Right. There's actually two answers there because of something called symmetry. Yeah, this is still part of question 2 right here. Right. We just found the SN1 product, but we did not find the E1 product yet. Well, the E1 product is going to be minor, but let's just do it for extra practice for E1. Yep. Oh, A and B. Hold up. Yeah, because this is going to be 1, 2, 3 tri-substituted. This is 1, 2, 3 tri-substituted. Oh, there. It's actually going to be all of them. All of them could make tri-substituted alkenes. Right. I'm just going to show you guys the mechanism of A first, and then I'll give you guys the products for B and C. Right. For this E1 mechanism, the ethanol is going to come in and act as a base and deprotonate that beta hydrogen. This bond between the carbon and hydrogen here is going to make a double bond right there. And there's no good living group to kick out. So we don't kick any good living group out right there because there's no good living group there. That's E2. Right. Okay, so that would give us this right here for A. Right. For C, if we do the same thing, this is the alkene we get right here. Right. Now, if we do C right here, this is the exact same thing as this because of free rotation of that single bond right there. If you rotated that single bond right there, these two groups would like rotate into each other's spots. So these two are actually the same thing. So you'll only get two products, two E1 products. This E1 product and that E1 product. E1, E1. And depending on the starting reactant, you could have one E1 product, two E1 product, or three E1 product, depending on what you have. Right. This third one here is going to be also a product, but it's the exact same thing as that right there. Right. It's the exact same thing because this single bond here can rotate. And then if we rotate that single bond, these two groups here will swap into each other's places to get to that product there. So they're the same thing. So it could be the third one. You could put this as the answer, but that's the exact same thing as this right here. Mm-hmm. Okay. Okay. Is the OH here? Yeah, the ethanol here will act as a base in E1, right? Because elimination is always going to be an acid-base reaction. E1, E2, they would always be acid-base reactions. This ethanol here is acting as a base because it's attacking a hydrogen. It's accepting a hydrogen. Right. How do you figure out where to draw the double bond? So the double bond is always going to be between the alpha carbon and the beta carbon, right? So it's always going to be between the carbon that had the carbocation and the carbon that you deprotonated, right? So it could be here, here, or here, right? We cannot make the double bond here because there's no carbocation here. We can't make the double bond here because there's no carbocation there. We can't make the double bond there because there's no carbocation there, right? We have to make it between the carbocation and the beta carbon. So it could only be here, here, or here. So for SN1, it's like nucleophile, then base, right? That's another good way to think about it. SN1 will always do a nucleophile first and then base, right? This ethanol or the weak base, weak nucleophile will act as a nucleophile first and then a base, right? But then for E1, it will act as a base. How about figuring out which side of the bond? Does it affect if it's cis or trans? Yeah, that's a good question actually, because it could have cis and trans products. Let me give you an example of that here. Okay, so we have a secondary substrate, weak base, weak nucleophile, and then looking at the chart, if you guys do a lot of practice problems on this, you guys like could just tell what reaction it is already. This is going to be an SN1 E1 reaction, but I'm going to focus on the E1 aspect of it to show the cis and trans product that you could form. The first step is the leaving group would leave first, forming a carbocation here. Wait, let me fix this up so then I can show you guys the cis and trans. I just realized there's a hydride shifter, like, right? Because whenever you have this carbocation intermediate right here, always look out for the carbocation rearrangement step, which we see that it could do a hydride shift here to form the more stable carbocation like that, right? And then at this point here, let's draw out all of the beta hydrogens. This beta hydrogen, this beta hydrogen, this beta hydrogen here. Okay, get rid of this ethyl group so then I could show you guys. No, that would not. Okay, what's wrong here? Why can I not do this right here? This leaving group leaving. What's the problem with this this step, this phase step? Right. Think about the stability of this carbocation here. A primary carbocation is too unstable to exist. So whenever you see a primary unhindered substrate and you see a weak base, weak nucleophile, no reaction happens. No reaction at all. Right. And I think that was one of your problems in the practice midterm. And that's because we cannot form a stable carbocation to exist for the reaction to go through. This is too unstable to exist. Right. But if we have that methyl group right there, then the reaction can go through because it's secondary. Right. There you go. Okay, so now we can choose A, B, or C now. And in this case, there's only one option that you can go for. Which one do you want to deprotonate using the water to form the more stable alkene? A, B, or C? Yep, A, right, because it's the most substituted beta hydrogen. So we're gonna deprotonate that A beta hydrogen. And we're not gonna make a double bond here, right? Because that's gonna break the octet rule. There's no carbocation there. But we are gonna make a double bond here, which will fulfill the octet rule. It goes towards the positive charge to form this alkene right here, right? Which is tri-substituted 1, 2, 3. Right. And this right here, we see that at this carbon, this is the highest priority group. This is the highest priority group. This is. Have you guys learned about E and Z alkenes yet? Like, or E and Z? Or just cis and trans? Oh, okay. Yeah, this is E because if we look at this carbon here, the highest priority group is this methyl group. If we look at the bottom carbon, the highest priority group is that ethyl group right there. Make a line through the double bond. If the two highest priority groups are on opposite sides of the line, right, then they're considered E. If they're on the same side, then they're Z, the same side, Z, the same side, right? We can make a Z alkene here because before this step right here, let's say that we rotated this single bond to get this intermediate right here. Positive charge, right? This single bond right here can rotate because this is not a double bond yet, right? It's still a single bond which can rotate. And if I rotate it, I'm gonna swap these two groups, the methyl group and the ethyl group. And if I swap them, they swap into each other's places like that. Right? And then I'm still gonna deprotonate the most substituted beta hydrogen to make a double bond there. But this one here is different than the previous one because this alkene right here is Z. And there are two different products. Right? Where E is going to be the major E1 product. Z is going to be the minor E1 product because of steric hindrance. Right? But they're both minor in comparison to SN1 products. SN1 product is always major over E1. Right. Why wouldn't C work? C would not work because if we deprotonated C, let's say, for example, like that hydrogen right here and make a double bond here, the alkene that we are going to get is this right here. And then, oh, yeah, C would work as well. This is tri-substituted. Tri-substituted. Right. But this right here is going to be the exact same as either this or this, right? And specifically, it's going to be, let's say, make a line here. Highest priority group on this carbon is this ethyl. Highest priority group on this one is that methyl. This is E. So this is the exact same thing as that, right? So A and C could both work, but they'll give the same exact product. This exact structure here is the same exact structure as that. Right, nice catch, nice catch. Okay. Because one carbon has an ethyl and methyl, the other carbon has a methyl. Same for the other one here, methyl ethyl, and the other carbon methyl, like that. Right. Any questions on SN1E1 so far? I think the hardest reaction in this is E2. Like E2 is very involved with the anti-periplanar trigonal state, like Hoffman rotating to make the anti-periplanar. But do you guys have any questions for SN1E1 so far? Number 10. Yeah. Let's see. Is this related to? Oh, okay. Yeah. This is related to the. Oh yeah, SN2 and SN1E1 stuff. Okay. So there we go. Yeah, so let's go over this and then the last problem on the practice midterm. Let me rewrite the E1 products for Caesar and then go on to those. Yeah. So for this one here, the E1 is either going to be this one or this one, E or Z, for this specific problem here. But if we go back to the one that we were doing earlier, the E1 is going to be these products here. And this one is specifically E because the two particle groups are on opposite sides. You can also draw the Z products, but that's minor. And I don't think you will have to draw the minor products. That's more of a Leibniz thing. But I don't think this professor will do that. Yeah. Based on what I've seen in this practice exam. Right. So number 10, this is a predictive reactant problem here. He already gave you the reagent and the product here. Right. I'm gonna redraw this as this right here to show that this is the N3 of this N3 minus right here, right? So what reaction do you guys think is going to be happening here? Just looking at the type of base and nucleophile here, the N3 minus. SN2 reaction, right? Because this N3 minus is a weak base, strong nucleophile, which is a strong indicator for SN2 reaction. And we said earlier that SN2 reaction does a backside attack, an inversion of stereochemistry. So we see that this was the carbon that got attacked. So we can say that it came from this carbon here that was a wedge to some kind of good leaving group. And you get to choose the good leaving group here. It could be Br, chlorine, OMS, OTS, OTF, any good leaving group that you choose. I'm going to choose bromine, right? You could choose chlorine, you could choose OMS, OTS, iodine, Ed, doesn't matter, any good leaving group, right? Where this N3 minus would just come in, attack that electrophile, and kick that out to get that product right there. Does that make sense so far? Any questions on this one? Okay. Yeah, so let's move on to this one and then the Fisher projection problem. Okay, so notice how we have a wedge bromine here in the reactant and then a dash bromine here in the product. There is only one reaction that you guys learned so far that inverts stereochemistry like that, which is SN2. So you know that there's going to be SN2 reaction somewhere in this reagent arrows, right? You do not want to just put NaBr, right? The reason why is because when you do a Br minus, attacking that electrophile carbon and kicking it out, you would get that like product here, but you'll also get a mix of the wedge product as well, right? The reason why is because when you put NaBr, that's going to be an excess, right? So a second equivalence of Br minus is going to come in, attack that carbon, kick that out, and get to that products here. So you get a mixed product of this and this. But you don't want a mixed products. You want a high yield of this product only, and only this product, not this product, right? So this is a trick for synthesis here. When you guys learn about synthesis problems, which is basically meaning that they will give you a reactant molecule, a product molecule, and you have to figure out what goes in between. And this could be multiple reactions like that would transform this reactant molecule into this product molecule. That's called a synthesis problem, right? So this could be multiple reactions that you have to put here. So we could do SN2 like one time, let's say with a good leaving group, like NaCl, right? The Cl minus is going to come in, attack that carbon, pick up the bromine to get this intermediate here with the Cl. And then right after that, we could do, let's say, NaBr. Take a step. where the Br minus can attack that carbon, kick out the leaving it chlorine to get to, oh, not yet, right? Because that would give us like the wedge product going backwards. So we don't want to do that. We could do NaI. Let's do NaI. Right. We couldn't do NaBr because that would go backwards with the wedge, but we don't want a wedge. We want a dash. Right. So the I minus will come around, attack that carbon, kick out the chlorine, and get the iodine right here. Right. And then the third step, we could do NaBr, which would give us to the final product that we want. So this was a 3-step synthesis problem here, which would give us to that dash bromine right there. Right. So three steps. Oh yeah. So DMF is an A product solvent, which would facilitate the SN2 reaction. So some professors don't require you to put the solvent to get full credit, but just put it just in case, because I don't know a lot about this professor. He might want you to put an A product solvent, which is DMF. You could also put DMSO, or you could even put THF. Any A product solvent that would work for SN2 reaction. Okay, yeah. So put A product solvent. A product solvent means that it would allow the reaction to go through. It would stabilize the charges for it to exist to be able to attack the electrophile, right? It would not do anything in the reaction, right? The DMF, DMSO, THF, it would not interfere with the reaction. That's not important. It's like just there. It's just there to have the reaction go through. Right, but we do not want a product solvent like water. If you put water, right, then a lot of partial positive hydrogens would surround the negatively charged chlorine and trap that chlorine ion and preventing it to attack the electrophile. Right, so that's why we don't want a product solvent. We want an A product solvent like DMF, DMSO, or THF with no H bonds to interfere with this reaction. Oh yeah, so I could have switched this as well. You could have said NaI first, and then this could have been I, and then the second step could have been NaCl, and then this could have been Cl, right? But the last step here has to be NaBr because of the product. The product here is bromine, so that's why the last step has to be NaBr. But these two could be interchangeable, right? Why couldn't I do NaCN as 1 or 2 step? Like why couldn't I do NaCN as the first or second step? So let's imagine I did NaCN, where the Cn minus attacks that carbon, kicks out the leaving group to get this product here. Right. Now let's focus on this Cn here. Is this a good or bad leaving group? Bad leaving group. Right. So when you try to do, like, let's say NaI or NaCl, it doesn't matter. Let's say NaCl. The Cl minus here would not attack that carbon. Well, it can, it tries to, because it's like kind of partial positive charge, but it would not kick it out. It cannot kick out a bad leaving group. That's why no reaction would happen. It would not go through. This is no reaction because we do not have a good leaving group. And you need a good leaving group for all of these reactions. You need a good leaving group for SN2, SN1, E1, and E2 reaction. Right. So that's why I use NaCl or NaI in order for us to have intermediates with good leaving groups for us to keep doing SN2 reactions like that. Bri and chlorine are strong nucleophiles and good leaving groups. Yes. And they are weak bases as well. BrICl, they're weak base, strong nucleophiles, and good leaving groups. Yeah. We cannot use Br directly because that would actually give us a mix of products. If we went Br directly, another equivalent of Br minus will attack that, kick that out, and form this product as well, which is the starting material reactant. And that gives us a mixture of products, which is not good for lab. Right? In lab, we want high yield products. And this will selectively go for this bromine with only dashes, right? Because imagine in lab, you put NaCl on this reactant molecule here only, you would have the reaction go through until all of the material in your flask or whatever the thing is in the reaction is going through is this structure here, right? And then you wait some time again, and then you put NaI in it until everything is this structure here. You wait some time again, and then you put NaBr until you get every single thing to be that product that you want right there, right? And that avoids mixed products. Right. Any questions on that part? Yeah. If you change this question to like let's say iodine, then you could do this in one step. You could just go from here to here using NaI, and that's all you need, right? Because the I minus will just attack this electrophile carbon, kick out the leaving group, invert the stereochemistry, invert the wedge to a dash, and have the iodine there. That would just require one step, which is NaI or Ki. Okay. But this is a little bit trickier because it has the same like atom as the reactant molecule here. Right. Yeah, does that make sense? Yeah, okay. Okay. So let's look at this last one here. We do have a good leaving group, iodine, and in a product, we have an alkene. And whenever you have an alkene as a product, what reaction comes to mind? Substitution or elimination? Elimination, E, right. Now, let's look at the kind of alkene it is, right? This alkene right here, do you think, like, because the alkene could have been formed like this, which it is in this case, or like this, right? The product they form, is it the more or less stable alkene than this alkene here that they could have formed? Less stable alkene. And then, do you guys know what reaction makes a less stable alkene? Would it be Zaitsev or Hoffman E2? Hoffman, right. So we know that we are going to do a Hoffman E2 reaction. And what kind of base? We know it's going to be a strong base, strong nucleophile, because that's what E2 reactions use strong base, strong nucleophiles. But what kind of strong base, strong nucleophiles will Hoffman E2 reaction use? A small unhindered base or a big bulky base to get the Hoffman product? Yeah, it's the bulky one, right? So you could use tert butoxide like this, right? You could have written it in its condensed formula too, but I like drawing it in the bond line form, right? The reason why this gives the Hoffman E2 product is because let's do that same trick, right? This is the alpha carbon holding the leaving group. These are the beta carbons. Draw out one beta hydrogen for each, right? We know that the left beta hydrogen is going to form the more stable alkene. So that's what it wants to do naturally, right? But the problem here is that because we're using a bulky base, there's not enough space or not as much space to attack that hydrogen and make the more stable double bond at once. Because it's so bulky, it's going to go for the most available hydrogen, the one with the least steric hindrance, the one with the most space for it to reach in and attack that hydrogen, make a double bond there, and kick out that leaving group. Those three arrows happen simultaneously. They happen all at once to get to this final product here. Right. So bulky base will go for the most available beta hydrogen, the one with the least steric hindrance, or the one with the most space to make the double bond and then kick out the leaving group at the same time. If we used a small unhindered base, then it would be able to reach for the more sterically hindered one to form the more stable double bond if we used a small base, right? But in this case, we're using a bulky base, which gives us the less stable double bond here. Right. Any questions on that part? Yeah, so let's go over the Fisher problem that someone requested earlier, and then do number 12. Fisher. Hmm. This one. Oh, that was 10 continued. This is the beginning of 10. Oh, shoot. Okay, segueing off of what we just did earlier, let's do this first one here, because this first one is going to be related to the one that we just did, right? We have a secondary substrate, OH minus, which is a strong base strong nucleophile. But is it a small strong base strong nucleophile or a bulky strong base strong nucleophile? Small, right? So it's gonna be able to grab the more substituted hydrogen and make the more stable alkene like that, right? That's because we're not using a bulky base. Now HCl and acetone, there's no good leaving group here. No good leaving group. And HCl, there's no alkene as well. So this is a strong acid. So you would look for something basic like an alkene or OH minus or something like that, but no basic atom is here on that molecule, so there's no reaction. No reaction. Because this strong acid cannot react with anything here. Like there's no basic atom here. Okay, now the Fisher projection of number 10. So the question says that we're gonna assume everything is in 1 mole, right? Unless otherwise stated. So this Cn minus here is in 1 mole. Now this is testing about your knowledge on leaving group ability. We have 2 good leaving groups here, chlorine and bromine. Which leaving group is better and why? Uh-huh. Yep. It does depend on the solvent, which is CH3CN here. Right. And this is a product solvent because there are no H bonds here. Right. No H bonds. So in a product solvent, what? Right. So this a product solvent thing, and the bromine minus halogen minus, like that thing is more for nucleophilicity, right? Where let's say fluorine, chlorine, bromine, iodine. Fluorine is going to be the best nucleophile. Oh, wait, wrong arrows. In a product solvent, right? But if you are in product solvent, it flips. The list flips. So this is a separate concept here. Right? This is in product solvent. Right. Now the reason why the list is like this is because we know fluorine is the smallest halogen and an iodine is the biggest halogen. Right. Which negative charge seems the least stable, right? Which negative charge seems the least stable? So the fluorine minus here is going to be the least stable because fluorine is the smallest atom. There's less space for this negative charge to move around, right? And because it's the least stable, it's going to be the most reactive, the most unhappy, right? But now if we move on to product solvent, let's do the same size scale. Cl minus, Br minus, I minus. Now I'm going to draw the H, like positive charge H's in purple like that. Right. The F minus here is because it's so small, H bonds are able to solvate around that ion, right? And then if you look at iodine, because it's the biggest, there's less of a solvation show on the iodine right there. And bromine is going to be something like that. And chlorine is going to be something like this. Right. So tighter solvation shell because of the smaller atom. And because of this tight solvation shell here, it prevents that fluorine minus from attacking. Right. This I minus here has a loose solvation shell, so this negative charge can attack. Right. So we could say nucleophilicity. Right. Stability. And we could say nucleophilicity is on the other direction here. They flip. Right. So in a product solvent, there's no solvation shell. The fluorine minus is the most nucleophilic because it's the least stable. The negative charge is unstabilized by like the small space that it can be in that small fluorine ion, right? But in product solvent, because of H bonds and solvation shell, the fluorine is now the weakest nucleophile because it's solvated by the H bonds there. Right. So that's the different concept. In this case here, bromine is the better nucleophile because it's bigger. It could hold the negative charge better. So the Cn minus is going to attack that carbon there and kick out the bromine. Right? And in Fischer projection, to invert the stereochemistry, we're gonna swap the two groups horizontally, right? So because the Cn minus attacked that right there, kicked out the bromine, the Cn is now gonna be on the right side, and that's showing the inversion of stereochemistry. Everything else stays the same because everything else was unreacted with. Nothing touched those carbons, so nothing will change on the other carbons, right? This chlorine here will stay as it is, right? This chiral center here with the bromine got reacted with, which is why it got inverted. If you calculate R and S, you will see that if this is R, it will flip to S. If this is S, it will flip to R. If it was two equivalents or an excess amount of NaCN, then the Cl minus would react afterwards. But he didn't say excess in this problem, so this is the answer after the first equivalence of NaCN, because it would choose for the stronger, the better leaving group. Oh, NaCN is in excess. Okay, yeah. So if it's in excess, then it would also react with the Cl. So the second Cn minus will attack that carbon, kick out the Cl, and invert it to swap the two groups like that. Right. So that's if it is in excess. But if not, then it would be the first one. Right. There. Right. This is the answer in excess. And this is the answer in one equivalence, 1 mole of NaCN. I would stick with 1 equivalence, 1 mole because of the directions here. And I don't see excess in the reagent here arrow because the professor would say excess, which would lead to this answer here. But because it didn't say excess or XS, then I would stick with this here. Or you could draw both and label them as like 1 equivalence and excess. Then that you'll show your TA or whoever grades it that you know that this is the answer in 1 equivalence, 1 mole, and this is the answer in excess. And you'll only have to worry about that if there are multiple leaving groups like this, right? In most of the reactions that you get, there's only going to be 1 good leaving group. So you only have to worry about that once. But because this has 2 good leaving groups, then you have to worry about which one's the better leaving group. Yeah, assigning stereochem and Fischer projection. Let's do that after we finish up 10 and 12. Okay. What reaction do you guys think this is going to be now based on the substitution, the substrate, and the reagent here? Right. Secondary, because it's attached to 2 other carbons, and then ethoxide. Ethoxide is what kind of base, what kind of nucleophile? Yeah, and it states 1 mole or 1 equivalent in the directions here. Yeah, assume all reactants are present in 1 mole unless otherwise stated, but it didn't state excess in the arrow. Yeah, strong base, strong nucleophile. And it's also a small one, small unhindered one, because it's not third butoxide, it's not LDA, which means that it can go for the more substituted beta hydrogen, make a double bond there, kick that out, get to this final answer here, E2. Right. And then whenever you see strong base, strong nucleophile, that's a big indicator for E2. Whenever you see weak base, strong nucleophile, that's a big indicator for SN2. If you see a weak base, weak nucleophile, that's a big indicator for SN1, E1. Right. And then you always have to look for the substrate as well, because weak base, weak nucleophile, SN1, E1, no reaction for primary unhindered substrates. Right? Because the first step of the SN1E1 mechanism is that the leaving group leaves first to form a carbocation. And the carbocation cannot exist on a primary unhindered carbon. Right? It's too unstable. For SN2, they require a less sub carbon for steric hindrance. And then E2, it could happen on a lot of things. This is the most tricky one. Okay, and this last reaction here is the very first reaction that you guys learned in OChem. I think this is midterm 1 material, free radical halogenation. And because this is bromine, it's the most selective one. It will select for the tertiary carbon, which we only have one here. So that would be the answer for that last one, though, bromine. There you go. So since nuclear philicity increases, we need to look for the atom that's nuclear philicity, or will it be a better electrophile? Are you talking about the leaving group here, like about the nucleophilicity of these ones here for this problem?
Yeah, so because I think you were talking about like different, it depends on like different solvents. So I just got a little bit confused with like
right.
yeah.
So this right here, right, with the A product solvent and product solvent, that's when you see on the arrow NaX, where X could be fluorine, chlorine, bromine, or iodine, right? That's when these are nucleophiles, right? But in this specific example here, the X or the halogens are not nucleophiles, they're leaving groups. So when they're leaving groups, ignore all of this. Ignore all of the nucleophilicity, A product solvent. Ignore that. Right? Don't worry about that. This like A product solvent stuff is only used when the nucleophile is an X minus, where X is fluorine, bromine, or iodine. Right? And the nucleophile is going to be on the arrow. The nucleophile here is CN minus, so we don't have to worry about that. Yeah. Does that make more sense? Yeah. Right. So the CN minus thing here, yeah, don't worry about this thing here. I have Kahoots on that, but I don't know if Ling will test on that concept, or if he taught it. Okay, so that's all of number 10. Let's do number 12. Okay, provide all products and arrows of fishing for the mech. Oh, so we did something very similar to this earlier in the session. Someone walk me through this. Someone walk me through this mechanism. Well, first, what is this substrate here? Is it primary, secondary, or tertiary? This carbon attached to the leaving group. Tertiary, right? Because that carbon there is attached to 3 other carbons, 1, 2, 3. Now, what kind of base and nucleophile is this methanol here? This neutral alcohol. Weak base, weak nucleophile, right? Which is a big indicator for what kind of reaction? SN1, right? Now, SN1 or E1, but SN1 can be the major product, right? So let's just go for the SN1 products. I don't know if he wants both, but let's just do both just in case. But SN1 is major. Okay, so what's the first step of this mechanism for SN1 E1? Get rid of leaving group leaves by itself, because the product solvent here, the partial positive hydrogens are going to surround it, make it leave. And get this carbocation right here. And notice how at that carbon right there, it used to have wedges and dashes because it was chiral. This carbon here lost its chirality, and now it's flat and planar. Everything is flat and planar. There's no wedge, no dash anymore. Right. And then at this point right here, do we have to do any carbocation rearrangement steps? Like, do we have to do hydride shift, methyl shift to make a more stable carbocation? No, we do not. Right. Because it's already in its most stable position. This is a less stable one. That's primary. This is less stable, secondary, less stable, secondary. So what's next here? What happens next? Right. So the deprotonation step for SN1 product reaction is going to be at the very last step. Right. There's no acidic hydrogen here to deprotonate because all of the hydrogens in this molecule here are attached to carbon. And because this is a non-polar bond, this hydrogen does not have a partial positive charge. Right. So there's no acidic hydrogen to deprotonate. The next thing would be that this methanol here will act as a nucleophile to attack that carbocation right there, to attack the electrophile. Right. And we said earlier that this is flat and planar. So when it attacks, it can attack on the top side, giving you this kind of product here, a wedge product, oxygen. And that oxygen is attached to a CH3 hydrogen, positive charge. That makes this methyl group a dash, like that. Or you could have this product here where the OCH3 attacks on the backside, giving you a dash, forcing the methyl group to be a wedge, like that. Now, this is where you do the deprotonation step. The CH3O minus OH will now act as a base and deprotonate that positive charge oxygen to get to the neutral answer here. Right, and we could have another base to deprotonate that. Right. To get this point here. Oh, wait, wrong one. There we go. Okay. Are these considered racemic mixture now? Yeah, it is. Right. Because we have a chiral center here and a chiral center here, and they're enantiomers of each other, and that's a 50-50 1-to-1 ratio of enantiomers. This is now racemic mix. The example that I gave you guys earlier was not a racemic mix because there were no chiral centers. But in this case, this is a chiral center. So this will give you a racemic mix. Yeah. Let me list out the basic steps for those things right here. So SN2 is the simplest one. It's one step. Backside attack. Nucleophile attack electrophile. E2 is also one step, so let me just do that as well. The base. Well, depending on what kind of base you have, right? Let's start with the more common one. Small, strong base, strong nucleophile. Deprotonate. Most substituted beta hydrogen to form double bond and kick out leaving group, all at the same time. All those three things happen at the same time. For E2, right? If you have a bulky base, then it deprotonates the least stable, least substituted beta hydrogen. because it's so bulky that it can only grab the one with the most space, which is the least substituted beta hydrogen, which would form the less stable double bond, giving you the Hoffman product. The small one will give you the Zaitsev product. SN2, there's gonna be inversion. Sterile. Yeah. The backside attack. Okay, now SN1, E1, it's multiple steps. SN1, E1. The first step, kick out the leaving group. And then the second one, look out for carbocation rearrangement. So a hydride shift or a methyl shift. Right. And after that shift, if there was a shift, then for SN1, the weak base, weak nucleophile attacks the carbocation, then gets deprotonated. Right. For E1, the weak base, weak nucleophile deprotonates the most substituted beta hydrogen to form a double bond. And I wouldn't worry about the cis and trans or EZ alkene because I don't think he'll tell you that. I'm not sure though, but yeah, I wouldn't worry about that for E1 because it looks like he's just focused on SN1, which is major over E1, right? So SN1 E1 is a multi-step reaction, and SN2 and E2 are one-step process. DB will be double bond. Yeah, so for number 12, right here, his answer that he put is the same thing as what I put here, right? If you assign R and S to his products and assign R and S to this, it's gonna be the exact same thing. It's just different representation, right? Like you just rotated the bonds differently, but it's the exact same thing. I just like doing it this way right here to show, to just make it more clear to see in the mechanism, right? But it's the same thing. SM1 will always be major over E1 unless heat is added, right? So if you see this triangle symbol or delta symbol, that's heat. If you see that under an arrow like water, then the E1 will be major. But if there's no heat, no delta symbol, then SM1 will be major. So in most cases, SM1 is major over E1 with no heat. Yeah. It's not necessary to rotate. It's just a different way to see it. Not necessary to rotate. Yeah, because if you draw the same exact structure but in a different representation, the professor or TA should give you this full credit for it, right? Because it's the same thing. It's just different representation. Like, and you'll see that more clearly when you guys do reactions as well, because like the way they draw things in the key could be different than what you drew, but it means the exact same thing, which they will still be able to read that and give you full credit for that. Okay. You guys want to do? Oh yeah, IR, huh? Let's do that. Let's do IR. And then Kahoot maybe, or any other problems that you guys want to go over at the midterm. Where's my spectroscopy stuff? Right here. Yeah, okay. Let's do number 5 and then number 6 on the practice midterm. Number 5. Okay, chairs. Okay, let me go over everything, or yeah, I hope I don't miss anything about chairs that you need to know. Okay, so chairs are going to represent cyclohexanes, 6-membered rings like this. Right, and they're going to exist in nature as chair conformers. So I'm going to put groups on here just to show the other concepts that I'm going to show you guys later on. Let's say this is a wedge methyl, and let's say this is a dash isopropyl. Right, and then the way I'm going to number this is I'm going to number this as 1, 2, 3, 4, 5, 6, and it does not matter how you number this. Yeah, no problem. Right. What matters is what you put on the atoms of the chair, right? So there's 2 chairs that you need to know. One chair is going to be this right here. The other chair that you're gonna see is this. Right. So my favorite chair is this left side here. And the way that I number it is this right here. It does not matter how you number it. You might have seen it in a different way, but this is how I do it. 1, 2, 3, 4, 5, 6. Right. And then when we rotate it to the other chair conformer, right, like this one to this one right here, we're going to rotate every single number clockwise. Right. So this one right here going clockwise is going to be over here, and it's going to go like accordingly, like 1, 2, 3, 4, 5, 6. Right. And if they give you this chair conformer and you should try to go to the other chair conformer, then you rotate everything counterclockwise to go backwards. Right. Counterclockwise this way. Clockwise this way. And the way that I like to remember this is that I like to think of this as a steering wheel, right? And then if you rotate your steering wheel clockwise, then you see that this bottom carbon is going to pivot up onto this carbon right here, right? Which is that exact same carbon right there. So that's how I remember like the numbering system of these chair flips right here. Right, now this is the axial equatorial. So axial bonds are going to be only up or down. That's the easier type of bond, right? So this is how I remember axial. I start at the top left corner. That's going to be axial up. I go to the next one on the bottom. That's down. So it's going to alternate between up, down, up, down, up, down, up, down. So next one's going to go up. Next one's going to go down. Next one's going to go up. Next one's going to go down, just like that. So those are all the axial bonds, right? Now for equatorial, it's going to be on the opposite direction as axial. So let's look at carbon 1 right here. Carbon 1 axial is going up, right? That means equatorial has to go down. And this is the most confusing part about equatorial. Like the way you draw it has to be like at a certain angle. And to find out the correct angle that you want, you ignore the first bond here. So ignore that bond and look at the second bond. It has to be parallel to that second bond right there, right? So ignore this first bond, ignore that first bond. It has to be parallel to this bond and that bond right there. Let's do the same for the second one here. This axial is going down, meaning the equatorial has to go up, which is going to be up in this direction. because we're gonna ignore this first bond right here, and then we're gonna look at the second bonds here, which is gonna be parallel to those bonds like that, right? Parallel to this bond, parallel to that bond, which is like that. Right? So do the same process for all of these other ones here. So to save time, I'm just gonna draw it, and let me know if you guys have any questions on this. So those are all the equatorial bonds, right? Ignore the first bond, parallel to the bond that it does not touch, the second bond right there, which is that equatorial bond right there. And axial and equatorial bonds, they're always opposite direction of each other. Right. Okay, so now when we do the chair flips, right? The axial direction and equatorial are gonna flip. So if we look at carbon 1 right here, what bond is going up, axial or equatorial? If we look at carbon 1 on this chair conformer here, like what's the bond that's going up in the up direction, the top direction, axial or equatorial? Axial, right? So that means on the other chair flip right there, the up has to be equatorial, right? So before we do that, let's do the same trick for axial. Up, down, up, down, up, down. That's all the axial. Equatorial, do that same trick. Opposite to the axial, parallel to the bond they do not touch. Like that. Right. Now, if we look at this other chair flip here at carbon 1, what bond is going up, axial or equatorial? Equatorial, right? So we see that at carbon 1, right, the up bond changed from axial to equatorial. If we look at, let's say, carbon 2, the up bond was equatorial on this chair conformer. When we flip it at carbon 2, the up bond is now axial, right? And that is an important concept because now let's piece in the groups that we have on this cyclohexane right here. At carbon 1, we have an isopropyl group, which I'm going to draw out as. Okay, so based on this right here, where is the isopropyl group going to be on this chair conformer, axial or equatorial on carbon 1? Based on what we see on the flat 6-membered ring. Would it be axial or equatorial? Equatorial, right. And the reason why is because this dash bond right here, it's going down, right? And then at carbon 1, the bond that's going down is equatorial. So I'm gonna put the equatorial right there. I'm not gonna erase the bonds so that you guys can review the notes after this, but I'm just gonna put hydrogens on all of these. You could erase the bonds when you draw these, but I'm just gonna put hydrogens here so you guys could refer back to this and draw out the conformer flips. Like that. Right. Okay. Hydrogen right here as well. Oh, wait. Carbon 3. Carbon 3 has something. A methyl group, right? And let's look at carbon 3 here. Where is the methyl group going to be at carbon 3? Axial or equatorial? Axial, right? Because this methyl group is a wedge, which means that it's going up. And at carbon 3 at this conformer, the thing that's going up is axial. So I'm going to erase the hydrogen right there to show that that's a methyl group right there. Yeah. This right here is a methyl group. Right. Let me just make it more clear by saying CH3. There you go. Yeah. Okay, now if we look at the other chair flip right here, at carbon 1, we want to maintain the same direction of the group, right? So at carbon 1, the thing that's going down is now axial. So now I'm going to put the isopropyl group as axial like that. The hydrogen is now equatorial. And at carbon 3, the methyl is up, which is on this chair conformer. The up is equatorial. So that's a CH3. Everything else are hydrogens. Hydrogen, 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 hydrogen. Okay. So I'm gonna highlight the groups more clearly to show you guys what's going on here. Okay, so notice how in both chair flips, the groups maintain the direction that they are supposed to be in, right? At carbon 1, the isopropyl group is down. And in both conformers, at carbon 1, the isopropyl group is down, down, and down. The only difference is if it's axial or equatorial. That's when you do the flip. The flip changes if it's axial or equatorial, but it always maintains the direction, right? The flip, maintain. My iPad is like so slow right now. Direction. But switches from axial to equatorial or vice versa. Right. If we look at carbon 3, we see an up methyl group going top on the top, which at this conformer, it's axial because that's the bond that's going up. And the other chair conformer, it's equatorial because that's the bond that's going up. So we maintain the up direction. We just switch axial to equatorial or equatorial to axial. Right. So that's how you do the flips. Now let's determine what's the lower energy one. Right. So lower energy means higher stability. Right? And to determine which one is a higher stability conformer, right? You first find your, we want, okay, here's the thing. This is, we want the bulkiest group, equatorial. That's the most important thing you look for. Bulkiest group, equatorial. And do you guys know the reason why we want it to be equatorial? There is a reason why we want the bulkiest group to be equatorial, to have more stability. Just to confirm, being up or down is what makes something cis or trans, and axial or equatorial successfully something with higher energy or lower energy. Right? Yeah, so axial and equatorial is used to determine about the lower energy conformer, but being up or down is what makes something cis or trans. But for cis or trans, right, you can only have exactly two substituents on the chair. If you have more than two substituents, like let's say you had another bromine dash here, then you cannot say cis or trans anymore, right? Cis or trans only applies to if the ring or alkene has exactly two substituents, right? In this case, we see that they're trans because one is facing up, one is facing down, which is also trans in this case right here, right? And this is because of less steric hindrance, or specifically less 1,3 diaxial strain. Have you guys heard about that term? If not, then I don't want to I'll go over it to overwhelm you guys, right? Because if you guys don't need to know it, then we don't have to go over it. Then have you guys heard of 1,3 diaxial strain? Yeah, okay. Okay, so 1,3 diaxial strain is basically saying how, notice how this bulky group here, that's axial, right? Let's say that's 1, 2, 3. The third carbon away from it, that hydrogen is also axial, right? And because they're both axial going down, they're gonna bump into each other because that's so bulky, and that's the 1,3 diaxial strain or steric hindrance. That's another way of saying steric hindrance. But it's a specific kind of steric hindrance, which is the 1,3 diaxial strain, which means that the two groups here, 1,3 to each other, are straining each other, bumping into each other. 1,3 because that's the relationship between those two groups. Diaxial because both of those groups are axial, two axial. 1,3 diaxial strain, steric hindrance. So that's the concept of 1,3 diaxial strain. Right. So which one of these will have lower energy, the left one or the right one? Yep, the left one. Because the first thing you do to determine this is locate your most bulky group, which is isopropyl, and then we want that isopropyl to be equatorial, which is the left one here. The right one, the right conformer, the bulky group is on axial, which is less stable, higher energy. Right. So this left one here has lower energy because it is more stable. Because it has less 1,3 diaxial strain. Lower energy, more stability, less 1,3 diaxial strain. Okay. So for this one right here, right, all of these methyl groups are equally bulky because they're the same exact group. So what we could do is do a process of elimination and see which one is incorrect. We see that 2 of the methyl groups next to each other are cis, right? So we have to find 2 methyl groups that are cis to each other, that are adjacent to each other. Right, so this one is going up, this one is going down, this one is going down. Right, notice how like there are no cis methyl groups adjacent to each other, so we could eliminate A right away, right? Because there's no 2 methyl groups that are in the same direction, right? This methyl group is going down, this methyl group is going up, this methyl group is going up. We can keep this option because we see 2 methyl groups are going cis to each other, that are adjacent to each other, so we can keep that for now. This is going down, this is going down, this is going up. We can keep that as well. This is going up, this is going down, this is going down. We can also keep that as well. Right. Now, let's eliminate the ones where we have a lot of axial bonds, right? This is axial, this is equatorial, this is equatorial, this is equatorial, this is axial, this is axial, this is axial, this is axial, this is equatorial. Eliminate C and D because C and D has 2 axial bonds, and D also has like 2 axial bonds, whereas B only has 1 axial bond. And the most one equatorial, which is going to be B in this case. Did you say dash is up and wedge is down, or does it not matter as long as they're opposite? Dash is down, right? So when you draw out the chair conformer, it should be going down, and wedge is up. But it's gonna be relative because when you do the chair flip, it's gonna be like these chair flips here, like even though like B is the answer, and we see that the 2 groups here are going down, right? Like this is going down, this is going down. But the answer, we see that those 2 methyl groups are cis to each other, they're going up. That's because you could flip the molecule upside down like that, right? If you flip the molecule upside down, this is what you get. Like imagine you have a model kit and you flip it upside down. You would get this structure here. Let's flip upside down like that. Right, now we see that the 2 methyl groups that are cis to each other are going up, which can represent these 2 methyl groups going up like that. Right, they're the exact same thing. It just flipped upside down like that. Right. Wait, I think it yeah. Yeah. So the most important thing here is to know the relationship between the groups, like the cis and trans. For this one is a little bit harder because there is no like bulkiest group. They're all equally substituted. So we want to find the one that has the most equatorial bonds, which is B in this case. Does elimination, like what you did, always work for each case? This is a weird example because we have the 3 of the same group, so it would work for something like this where all of the groups are equally substituted. There's no bulky group, so it would work for that. It will get easier. Like it's easier with this example here, where there is a clear bulky group, like isopropyl or tert-butyl, right? Then all you have to do to determine the one that has less energy is the one that is going to be equatorial, right? But if they're all equally substituted, there's no bulky group, then you find the one that has the most equatorial bonds to be less stable. And then that's how you do the elimination thing. We eliminated this one, A, automatically because the stereochemistry does not align, right? Like there's no two methyl groups that are cis to each other and adjacent to each other, right? This is up, down, up. Now we eliminated C and D because they both have two axial bonds. 1, 2. That's why we got like rid of those, because axial bonds makes it less stable, make it have higher energy. Whereas B only has one axial bond, the least amount of axial bonds, making it have more stability or less energy, right? Okay. So you guys wanted to go over one more. Let's do, yeah, one more column here. Or IR, actually, yeah. So here's the chart on like what you need to know for IR. 1500 and below is the fingerprint region, right? That's the region you can ignore. If you see a sharp peak at 1600, that's the alkene functional group. If you see a sharp peak at 1700, that's a carbonyl or a carbon double bond oxygen peak. If you see a sharp peak around 2100 to 2300, that's the triple bond region, right? Triple bond region, which could either be the alkyne or nitrile. If you see this base peak 3000 right here, that's the regular sp3 carbon hydrogen peak right there. So it's almost always going to be there at 3000. That's the baseline. To the right of that, if you see a sharp peak there, then that's an aldehyde peak at 2700. A little bit to the left of that, if you see a sharp peak at 3100, then that's an sp2 carbon hydrogen, right? sp2 carbon hydrogen is going to be something like this right here. This is an sp2 carbon hydrogen bond because that bond is in between a carbon and hydrogen bond, where that carbon is sp2. Right. Now, if you get to the 3300, 3300 range, this is where the broad peaks occur. If you see only one broad peak like that, then that's an alcohol or a secondary amine. If you see a big broad peak that merges with the 3000 baseline peak, then that's a carboxylic acid peak right there. If you see a fang, like a fang-like looking structure, two like fangs like that, then that's a primary amine structure right there, right? And if you see a sharp peak at 3300, then that's the terminal alkyne peak right there. So I would include this in your note card as well. This alongside with the SN2, SN1, E1, E2 reaction chart. Right. Yeah. Let's look at the reaction chart. Okay, and then to end off the session, do you guys want to do a Kahoot on one of the topics I have? NMR. Did you guys, is HNMR included in the exam? It's not. Okay, yeah. Yeah, so do not include HNMR for this midterm. Yeah. We can go over that HNMR thing in my future office hours, which is Monday, Tuesday, Wednesday, Thursday, 9 to 10 p.m. or the final review session sometime later. But I will have office hours tomorrow and Monday, Tuesday, Wednesday, Thursday. So the product solvents are going to be water and alcohol. That's the product solvent that you need to know. Right, that's the easy way to remember the product solvent. For a product solvent, there's a lot of them. Let me see. A product. Okay, just recognize DMF DMSO, THF, CH3CN, yeah. Just know those four. Those four are the most common ones I've seen. Yeah. Assigning R and S on Fisher projections. So let's do that. Okay. So let's say we have, okay, let's do 2.
Está marcando la mureta. Quiere que la vea.
Okay. So let's do this. Okay. So Fisher projections, whenever you see that, right? Think about the vertical line as all dashes. And then think about the horizontal lines as all wedges. So I think of it as like a person reaching out its arms for a hug. Right? Like these are the arms reaching out towards you because it's facing out of the page for a hug. So that's the first thing I would do when assigning R and S for these Fisher projections. Right. Okay, so now let's look at the first chiral center here, which is gonna be this one. Right. This is gonna be number 1 because oxygen is the higher atomic number. Now we have a tie between this carbon and this carbon right here. If there's a tie, look at what's attached to it. Right. What's attached to the bottom carbon right here is a carbon and 2 hydrogens. Right. So carbon and 2 hydrogens. Same as for this carbon here. It's attached to a carbon and 2 hydrogens. If there's a tie, then you look at the next one here, which is going to be this carbon here. This carbon here is attached to 3 hydrogens. 1, 2, 3. This carbon here is attached to a bromine, a carbon, and a hydrogen. The bromine takes priority over the hydrogen, so the bottom one is going to be priority number 2. This is going to be priority number 3. Hydrogen is the lowest priority number 4. But whenever we do R and S, right, we want the lowest priority group to be on a dash. But because hydrogen is on the dash, it's on a wedge, we do everything normally. So 1, 2, 3, going this way. It looks R, but is actually S, right? So this chiral center here is S right there. Does that make sense so far? So it's gonna be the same for all the chiral centers for the Fisher projection, but that's how you do it. If the lowest priority group, which is most likely the case on a wedge, right? Do everything that you do RNS normally, 1, 2, 3, right? And then you flip that at the end. So once we did that, it looks like R, but it's not actually R. It's gonna be S because the lowest priority group is on a wedge. And you can only do that flipping technique if the lowest priority group is on a wedge. So that is S. So that's how you do it in Fisher projections right there. Right. And I'll have you guys practice it for this chiral center, for that Fisher projection, and then these chiral center, that chiral center there. Yeah. Uh-huh. Okay. So on the reaction chart, why is SN2 and E2 both major? SN2 and E2 both major. Oh, so this is more specific for a primary hindered substrate. So the difference between a primary unhindered and primary hindered substrate is that this is a primary carbon because it's attached to only one other carbon. This is also a primary carbon because it's attached to one other carbon. But the carbon that it's attached to, if there's like more than one group, then that's considered primary hindered. If there's only one group, then that's primary unhindered. For the primary hindered case, right, SN2 and E2 are both equally major because if you do SN2, right, you gotta substitute the leaving group with the nucleophile. If you do E2, then you're gonna make this double bond right here. That's geminal, right? Whereas in the primary unhindered case, SN2 is gonna be major because it's not substituted. It could substitute the leaving group like that. But if you do E2, you're gonna get rid of the leaving group and put a double bond right there. And this double bond right here is minor because it is mono substituted, right? Whereas if you put a double bond right here for E2, this double bond is di substituted, which is stable enough to compete with that. But that's way too niche and specific, so I wouldn't worry about that. That example there. So I hope that makes sense. So like the primary hindered ones would favor like E2 and C2 more likely because it's more substituted for the alkene to exist. So if H is in the plane, there's just a line instead of you wouldn't flip it like RCS, right? If the H is just a line, flat and planar, then you can't do that technique where you flip it at the end, where you do everything normally and flip it at the end. You have to rotate the bonds. Yeah, you have to rotate to somehow to make it dash. And I did go over that example on the last session, which is on my YouTube. If you can watch that, it's also timestamped as well. I went over a lot of examples with that. That type of problem there. In my office hours. Okay. Do you guys want to try one Kahoot game before ending the session? We could do. Do you guys want to do IR or do you guys want to do free radical halogenation and chair flips? Yeah, because I think that's relative for this upcoming midterm, or even stereochemistry, like enantiomers, diastereomers. We didn't go over that. We could go over stereochemistry as well if you guys want, because I did not talk about that today. Okay, let's do that, and I'll talk about it while we do the Kahoot. Let's do it. Well, I kind of did with the chiral center enantiomers and stuff like that, but I didn't go over diastereomers, mesomolecules, not the same, identical. We'll go over that here. Okay.
Sorry.
Okay. I think there's one more, I think. Oh, there. Okay, let's just get started right now. Which one of these is?
Ling bagian.
Okay, so to assign priority, right, of like chiral center, look at the very first atom attached to the chiral center. That's the thing you look at. If there's a tie, then you look at the next atom, right? The very first atom for the red one is carbon. The very first carbon for the blue one is also carbon. Then we see what's attached to it. The red carbon is attached to oxygen 3 times because COOH is a carboxylic acid. And then if you look at the structure of a carboxylic acid, there's a double bond to oxygen and there's a single bond to oxygen. So it's bonded to oxygen 3 times, right? But the right one, that carbon is attached to a fluorine 1 time and a hydrogen 2 times. And fluorine has a higher atomic number than oxygen, right? So the hydrogens there are just there to trick you. Fluorine beats oxygen in atomic number, right? So fluorine would make that the higher priority group. Right. Nice, yeah. Br, higher atomic number than oxygen. So this one right here, look at the very first atom again, which is carbon. Then you see what's attached to it. For the red one, that carbon is attached to carbon 2 times because of the double bond and a hydrogen 1 time. So 2 carbons and 1 hydrogen. For the red one, that carbon is attached to carbon 3 times because of the 3 methyl groups, right? So 3 carbons versus 2 carbons, the 3 carbons win. So that's why blue has higher priority than the red one because it's attached to more carbons or more atoms with a higher atomic number. So this is a tricky one because for the blue one, you see an oxygen there and you automatically think that oxygen has a higher atomic number than carbons and hydrogens, right? But that oxygen is way too far away. When we assign priority, we always have to look at the very first atom attached to the chiral center, which is carbon and carbon in this case. But for the red carbon, right, the red side, that carbon is attached to 2 carbons and 1 hydrogen. For the blue carbon, that first carbon is attached to 1 carbon and 2 hydrogens. The 2 carbons beat the 1 carbon, so red would win. The alcohol wasn't even accounted for because the alcohol is too far away to account for. We only get to the alcohol when there's a tie, like a tie, a tie, a tie, a tie, a tie, and then until we hit that alcohol, that's when we take into account the alcohol, right? Yeah, so this right here, there are two chiral centers. That one chiral center at the top right corner is one because it has 4 different groups attached to it. The bottom left one as well. There have 4 different groups attached to it. Right. But here's another question. Is this overall structure chiral or achiral? Achiral. Achiral, right. Plane of symmetry. There's a plane of symmetry. There's a plane of symmetry down the middle, making it meso. Meso. So overall structure is achiral, meso, but there are chiral centers in that structure, which are 2. Meso molecules will have 2 chiral centers and a plane of symmetry. Oh wait, we just went over this. Yep, nice, nice. Yeah, we went over this too. Shoot, I forgot. Mirror plane, same as plane of symmetry. Yeah, same thing. Mirror plane is the same as plane of symmetry, which in this case, the plane of symmetry is diagonal like that, like cutting in between the 2 chiral centers, because everything on that bottom side is the same as that top side. And if there's a plane of symmetry, the overall structure is automatically achiral. There are 2 chiral centers, not 3, because chiral centers will only be on carbons that have 4 different groups attached to it. That nitrogen right there is not a carbon, so it will not be considered a chiral center. Right? It does have a pair of electrons, but when you get into 118C, you'll know that pair of electrons can invert back and forth into like enantiomer. So that's not a carbon, so don't worry about that. The chiral centers would be only on carbons with 4 different groups attached to it, which is the one with the wedge and the dash. Right? Alcohol. Right, not the dash on the nitrogen. The nitrogen is not considered a chiral center because it's not a carbon. Yeah, it's a non-carbon atom, heteroatom. Yeah, nice. No plane of symmetry, no mirror plane. Yep, overall chiral. For something to be overall chiral, it needs to have at least 1 chiral center and no plane of symmetry at all. Uh-huh. 3 chiral centers, right? And the 3 chiral centers are on that wedge with the OCH3, that's one. The second one is on the ring with the dash. And then the third one is the wedge methyl next to the aldehyde. So those are the 3 chiral centers there. Right. The one that most people might have missed is the one on the ring with the dash. That's a sneaky one. Nice. No plane of symmetry. Yep, at least one chiral center, no plane of symmetry, overall structure, chiral. This is a tricky one, right? Because even though there are wedges and dashes, it does not mean that that carbon is always chiral. The one with the wedge, methyl, that carbon has 2 methyl groups. So that's not a chiral center. The one with the dash ethyl, that carbon has 2 ethyl groups, right? So that's not chiral. So there are 0 chiral centers in this whole structure here. Okay, like if you see wedges and dashes, don't automatically assume that that is a chiral center. Look at if there's any other group like that, right? Yeah. I remember this one being a really weird one, so this might be. Okay, one of this is really weird about the mirror plane. Yeah, this was the weird one right here. This was the weird one. Right, so the plane of symmetry here is actually by the 2 ethyl groups, right? So look at the bond between the aldehyde carbon and the carbon of the 2 ethyl groups, right? The plane of symmetry is going to run through that bond, right? Because if you have that plane of symmetry there, you could rotate that bond. If you rotate that bond, then every single group is going to be like rotating around that structure right there. Right. This is like one of the weirdest examples I've seen. I've never seen this get tested, so don't worry about this example. But there is a plane of symmetry at that bond because when you rotate it, keep the ethyl groups stationary, like still. If you rotate it, the chain on the left is gonna rotate like this, like a tornado, right? And then that's gonna have that plane of symmetry right there. But don't worry about that. I don't think that's gonna be tested. That was the weird one. Yeah. Overall achiral because there are no chiral centers at all. No chiral centers, automatically achiral. Yeah, so this one right here is going to be R because we have a chiral center, which is at that carbon with the alcohol wedge, right? If we assign priority, that oxygen is going to be number 1 because it has the highest atomic number. The number 2 priority is going to be on the left side, right? The one with the 2 methyl groups, not the one on the right side because that bromine is way too far away. We always look at the first atom attached to that chiral center, which is the one on the left and the one on the right. They're both carbons, so we look at what's attached to them. The one on the left is attached to more carbons, 2 carbons. The one on the right is only attached to 1 carbon. So 1, 2, 3 going that way is clockwise, and that's R. And we keep it as R because the lowest priority group, hydrogen, is on the backside already, the dash. So I think people messed up here where they put number 2 on the bromine side, right? But that bromine is too far away to be accounted for. You have to look at the very first atom first, and then if there's a tie, you look at what's attached to that, and then keep going, and then you could touch the bromine if there is, yeah, what ties like that. So this one is R because the chiral center is going to be on the carbon holding the dash. The number one priority is going to be the bottom one, the one attached to the fluorine, right? Because if you look at the very first atom attached to the carbons, they're all the chiral center, they're all carbons, carbon, 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 right? Then we see what's attached to the carbon. The one attached to the one on the bottom is a fluorine, right? The one attached to the right side are 2 oxygens. The one on the left side is 1 oxygen. Fluorine has the highest atomic number compared to those oxygens, making that number 1. The number 2 is going to be on the carbonyl, the aldehyde one, because that carbon is attached to oxygen 2 times because of the double bond, right? And then the one on the left is number 3. So going that way, counterclockwise is S, right? But it's not actually S. It just looks S, but we have to flip it to R because the lowest priority group is on the front, on a wedge. So it looks S, but we flip it to R because the H is on a wedge. So we flip it at the end. Tricky, tricky. Ooh. Mixed answers. Okay, so these are identical chiral, and there are 2 ways to go about this question. One is the 100% for sure way to do it, to know that you get the right answer, and the other way is a riskier way, but it saves time and but there's a chance of getting it wrong, right? Is you guys think about it 3D about the risky way, but to do it the 100% correct way is to assign R and S to all the chiral centers, right? We see 2 chiral centers on the left side and 2 chiral centers on the right side. If you assign R and S to both chiral centers, they should be the same. If they're all the same, then they're identical, right? But let's say they all flip. Like let's say on the left side it was RR, and then on the right side it's SS. If all chiral centers flip, then they're enantiomers. Every single chiral center change, enantiomers. But if only some change and some stay the same, like let's say it was RR on the left side, and then on the right side it was RS. If some change, if some stay the same, then those are diastereomers, right? But in this case, it's gonna be identical because if you do R and S for these chiral centers, you're gonna see that they both stay RR and RR, or SS and SS, whatever it is, or RS, RS, right? Now the risky way to figure this out is to flip the whole molecule upside down like that, like a page of a book, right? If you flip it upside down, the backbone will stay the same, but the stereochemistry of the groups would change. If you flip it like a book, the bromine wedge will flip into a dash, the alcohol will flip on the other side, and the wedge will flip into a dash as well. It's the exact same molecule, just flipped around. So that's the identical molecule right there. It's just flipped like that. And you'll see that through assigning RNS for these chiral centers. So I would recommend doing that on the test. Yeah. Okay, last one. Yeah. And then for this one, I think the risky way is a little bit easier to see and do. What time is the midterm tomorrow? 8 a.m. Oh shoot. Oh no. Because it's gonna take time for Zoom to process this video and then upload it to YouTube and then put the timestamps in. So, oh dang, that's so early. 50 minutes to do it, or an hour and 20 minutes? An hour. Yeah, these are diastereomers. If you did the for sure way to do it, you'll see that some chiral centers changed, some did not. Like RR to RS or SS to SR, or you can see that the if you flip it or something like that, you see that one is a wedge, one is a dash, the other one are just both wedges. Some change, some stay the same. So that's diastereomers right there. Nice. Exam seems longer than the first, yeah. For 118A, I would say the hardest concepts would be SN2, SN1, E1, E2, and the HNMR for sure. After the HNMR, SN1, SN2, SN E1 stuff, you can learn about alcohols and ethers. Alcohols and ethers. Yeah. Okay, nice. Yeah, well, good luck on the midterm. Yeah, midterm tomorrow, guys. You guys got it. Huh? Yeah, no problem. Oh yeah, thank you. My second quiz is this Friday. I gotta study for that. Thank you. I'm gonna need it.